Hello everyone, I welcome you all at India's most comprehensive preparation platform for all competitive exams, that is BYJU'S Exam Prep. So very good evening. So in today's session we are going to discuss about functional dependencies and what is the importance of functional dependencies in relational database management system. So that's what we will understand in today's session. Okay, so this is a brief introduction of myself. My name is Vishal Rawatiya. I have 10 plus years of teaching experience and these are the achievements and areas of expertise. Okay, so there's a very important announcement for all of you that BYJU'S exam prep team is coming with the BYJU'S Premier League for CS. It is soon going to start, and this series is basically a YouTube plus app based series in which we will discuss the concept on the YouTube and we'll ask you to participate for the quizzes on the application. So that access to the quiz will be absolutely free. You just need to register using your mobile number and you will be able to access the quiz. So this is very important. So just go through all the YouTube upcoming sessions and check when the sessions are going to start by which faculty at what time. So please make a note of that. Okay, so one more important announcement is that on 25th of June at 9 a.m. BYJU'S exam prep is going to conduct a national scholarship test for all GATE aspirants. Do participate in this test and you may avail up to 90% off on all our programs. Okay, so this is everything about BYJU'S exam prep. Now let's start with the topic. Sir, what is functional dependency? So let's try to understand. If you have seen database management system, if you have studied database management system before, then you must have come across things like this. So there are certain things which are written in this particular format, AB implies CD. So this is actually nothing but functional dependency. So why do we, what is the functional dependency? So functional dependency is a relationship between two sets of attribute in a relational database. So this AB is one set of attributes. So it may contain one or more than one attributes. And this is another set of attributes. So this functional dependency is actually depicting the relationship between AB and CD. So whatever is on the left hand side is known as determinant and whatever is on the right hand side is known as dependent. So what's the idea? It states that the value of one attribute is completely determined. Value of one attribute. Which attribute? The value of one attribute, that is dependent attribute. This is dependent attribute, is completely determined by the value of another set of attributes. So this can be determined by this set of attributes AB. So why it is writing only one attribute? Because you can eventually further divide it into two parts. You can actually say AB implies C. So the value of attribute C is completely determined by this attribute C, attribute set AB, as well as the value of attribute D is also completely determined by the attribute set AB. So we can eventually further split it, that we will understand in the splitting rule when we will discuss it in the today's session itself. So it is just the beginning. I'm just trying to give you the intuition of functional dependency, that yes, so this is the dependent, right? So it's completely determined by the value of another set of attributes. In other words, what can we say? It's the definition. If a determinant attributes value is known, so if you know the value of attributes A and B, then you can provide the values of C and D, right? So this CD can be determined if you already know the value of AB. So values of C and D can be deduced based on the values of A and B if the values of A and B are already available. So what does it mean? So whenever A and B, for a particular value of A and B, the value of C and D will be fixed, that okay, this is the value for CD. So this is the functional dependency. We will understand more, but let's try to understand the formal definition of functional dependency. What's the formal definition? Let capital R be the relational schema. So let's assume that this is a relation R. This is some relation R. First of all, try to understand, I will not define the FDs based on the relational instance. I'm just trying to explain the concept of FDs with the help of relational instance, but it does not mean that the FDs are completely dependent. FDs are defined based on the relational instances. No, relational instances will depend upon the FD, but FDs are not defined by the relational instances. Yes, based on the relational instances, you can write out some FDs that this FD is not possible, right? So that's a different thing. So let's assume that this is a relation R. Now, in this, we can have one attribute set X and another attribute set Y. So this may be the combination of multiple attributes. Similarly, this Y also may be the combination of multiple attributes, because X and Y are attribute sets. So they may contain more than one attribute. So this is a relation schema with X and Y as the attribute sets over relation R. So X is one attribute set. Let's assume that this is nothing but A, B, C. And this is something D, E, F. Need not be equal. So don't say, sir, should they be equal in X as well as Y? No. Any relationship. So functional dependency X implies Y exists in R only if. So for R to exist, so let's try to understand. This is only if condition. So it means if functional dependency X implies Y exists, then this condition will be true. If functional dependency X implies Y exists, then this condition will be true. It does not mean that whenever this condition is true, functional dependency X implies Y will exist. No, right? So what does it mean? So let's try to understand. Let's have the single value X and single value Y so that we can understand in an easier manner. So it is just saying that the function, if functional dependency X implies Y exists in R, then only if it is using, therefore if will go there and then will come here. Right? Then for all tuples T1, T2 belonging to R, for all tuples, for any two tuples T1, T2 belonging to R, if the values of X are equal, so let's assume the values of X are X1 and X1 in this case, right? Then let's assume the value is Y1 and Y1. So you will say, okay, good enough. So whenever in two tuples T1.x is equals to T2.x, then T1.y should be equals to T2.y. So if X implies Y exists, if X implies Y exists, try to understand this. I'm going to say that this FD does not exist, but let's try to understand first that if X implies Y exists, then whenever the values of X will be same, the values of Y should also be same, right? So whenever X1 is appearing at the attribute set X, the same value should appear. This need not be Y1, so it may be anything element, but if at the place of Y1 element is present, then at this place also element should be present. So that's the idea. So yes, so for these two tuples the condition is satisfied. For these two tuples condition is satisfied, but let's assume that there is another tuple S2, for that also the value is Y1. So is it justified? Yes, this one is justified. Why is it justified? Because if in two tuples, if values of X are same, then the values of Y should be same. It does not say that if the values of X are not same, then what should happen with the values of Y. So this is also okay. So these things are okay. But if there is one more tuple in which X1 and let's assume there is Y2, X1 and there is Y2. So you may say, sir, there are two tuples T1 and T2 such that if T1.x equals to T2.x, then T1.y is also equals to T2.y. But no, it should be true for all the tuples T1, T2 in the relation R. So if we take this as T2 and if we define this as T1, then in these two tuples, when T1.x is equals to T2.x, T1.y is not equals to T2.y. Can you see T1.y is not equals to T2.y? So if this condition is not satisfied, then X implies Y will not exist. So we can eventually eliminate the FDs based on this definition, but we cannot provide the FDs based on this definition. Why? Let's try to understand. Functional dependencies will be defined by analyzing the database or analyzing the attributes of the database. Functional dependencies are not defined based on the relational instances. functional dependencies are not defined based on the relational instances. So if this is the relation R, whichever is in front of you in this blue color, if this is a relation R, then T1 dot Y and this is T2 dot Y, these two are not equal, these two are not equal, therefore X implies Y does not exist in R. This X implies Y does not exist in R. Have you understood the concept that I started by saying something else, but I am proving the completely opposite thing? So that's the idea, because it says if functional dependency X implies Y exists in the R, if this exists in the R, so then this condition must be true. Then this condition must be true. So if X implies Y exists, then this condition should have been true, but we can actually see that for this two tuples C1 and T2, this condition is not satisfied. Therefore, X implies Y does not exist. X implies Y does not exist in the relation R. Clear? I hope this thing is clear to everybody. So this is just the formal definition. Now let's try to understand the different types of functional dependencies. So let's look at this. Let's say this is your relation R, which consists of certain attributes A, B, C, D. Now, if I write something like this, AB implies A, then such type of FDs are known as trivial FDs. So let me define the trivial FD. What do I mean by functional dependency? So what's the objective? So if you have understood the objective of functional dependency, you will be able to say that okay, these FDs are trivial. So what does it mean? So what did we say? If we know the values of determinant, then we can tell about the values of dependent. So if we know the values of AB, then we can definitely tell about the values of C. Then AB implies C exists. Now, look at this particular situation. If you know about AB, then you can tell me about A. You already know about A as well as about B. So you can definitely tell me about A. Therefore, this dependency will definitely exist. This is not a big deal. If you already know about A and B, then you can tell me about A. What is the new information obtained by this statement? So this is a trivial thing, right? So what do I mean by trivial FDs? So just assume let X and Y are two attribute sets. Let X and Y are two attribute sets over relation R. So FD X implies Y. Let's look at this. I'm saying that okay, this exists. FD X implies Y is said to be trivial FD X implies Y is said to be trivial if X is a superset or equals to Y. If X is superset or equals to Y. So if X is superset or equals to Y, so yeah, clear? So this is the idea. So in this case, this is your X, this is your Y. You can actually see AB is superset or equals to A. Therefore, AB implies A is a trivial. Got the idea that you are not providing any new information with the help of this FD. You are only giving me the information which is already known to me. So you are not giving me anything new. Got it? So this is the definition of trivial FD, that if X and Y are two attribute sets such that X implies Y exists and X is a superset or equals to Y, then this is a trivial FD. You just need to understand one thing, that trivial FDs will be implied in every relation. All trivial FDs, you can say, trivial FDs are always implied in the relation. Or always valid in the relation. Why? Sir, again, something which is by default true, that will always be true. So you are saying whenever, so let's try to understand. You are saying whenever the value of A and B are same, the value of A should be same. Anyway, you are saying the value of A and B are 1 and 2, then in this tuple the value of A will be 1 only. Again, if you are saying value of A and B are 1 and 2, then again the tuple the value of A will be 1 only. It's not going to change. So whenever these two are same, the value of A will also be same. Therefore, you can eventually understand that this will always be a valid FD. This will always be a valid FD. This cannot be dissatisfied ever. Got the idea? So trivial FDs are always valid in the relation. There is no trivial FD which is invalid for any type of relation. So trivial FDs are always valid in every relation. So this is just for the purpose of understanding. I hope you have got the glimpse that what was I trying to say. So this is trivial FD. Now let's move to the non-trivial FD. Let's move to the non-trivial FD. So let's look at this. Let X and Y are two attribute sets over relation R. So we have two attribute sets X and Y. We want this to be non-trivial. So something useful must be given by this. Something. Hello GTZ, very good evening. So something useful must be given by this functional dependency. So, if don't say if. So let's assume let FD X implies Y exist in R. Let FD X implies Y exist in R. So there I directly said that in FD X implies Y if X is the superset of Y, because if X is the superset of Y, that X implies Y will definitely exist in the relation. But here first of all it should exist. Let FD X implies Y exist in the relation R. FD X implies Y is said to be non-trivial FD X implies Y is said to be non-trivial if and only if first what X is not a superset of Y. Yes sir, this is obviously understood, because if X is a superset of Y, it will become trivial, it will not remain non-trivial. And one more condition is there, that there should not be any common attribute between X and Y. That is, the attribute set X intersection with attribute set Y should be equals to phi. There should not be any common attribute between X and Y. Got the idea? So what are you trying to say, sir? So let's understand with the example. So if you have something AB implies C. If you have something AB implies C, then you can actually see AB, sorry. If and only if this is not, X is not a superset of Y. Come on. So X is, because if X is a superset of Y, then ultimately if X is a superset of Y, then this condition is not possible, because X intersection Y will be exactly Y only. It cannot be phi. So X has to be, X should not be superset of Y, because if X is a superset of Y, then X implies Y will become trivial. So AB implies C. So you can actually see that AB is not a superset of C. Good enough, because C is not present in the AB. And you can actually see AB intersection C is equals to phi. So both of them are present, therefore non-trivial FD. So what does it say? It tells me that if values of A and B are known, then I can give you the information of attribute C. If the values of A and B are known, then I can give you the information of C. But sir, why this X intersection Y condition is important? Okay, let's try to understand that as well. So let's see. AB implies BC. Let's look at this. Why don't we only say that X is not a superset of Y? So let's look at this. In this case, AB, is AB a superset of BC? Does all the attributes of B and C are present in the LHS? No, sir. So AB is not the superset of BC. So the first condition is true. But what is AB intersection BC? Sir, AB intersection BC is equals to B, which is not equals to pi, which is not equals to pi. Therefore, I believe you should have my image here. Therefore, not a non-trivial FD. Therefore, not a non-trivial FD. So, sir, then what is this? Then what type of FD is this? So, it is neither trivial nor non-trivial. Then what type of FD is this? This is actually defined as semi-non-trivial FD. This is actually defined as semi-non-trivial FD. Why? Some portion of this FD is non-trivial and some portion of this FD is trivial. Why do we call it semi-non-trivial? Some portion of this FD is non-trivial. So you can actually see in the previous example that AB can determine C is a non-trivial part, that AB is actually capable of giving the information of C. So it's a non-trivial part. But AB can give you the information of B. It's a trivial part, because AB can always give you the information of B, because the value of B is already known in the determinant itself. So yeah, okay. So that's the idea. So what is semi-non-trivial FD? So just note down the definition. Let X and Y are any two attribute sets. So I'm directly writing X implies Y is a semi-non-trivial FD if and only if the condition, if and only if first X should not be a superset of Y, because if X is a superset of Y, it will become trivial. It will become trivial. And second, what? X intersection Y is not equals to pi. So if X intersection Y is not equals to pi, then this FD X imply Y consists of some trivial portion as well. This FD X imply Y consists of some trivial portion as well. Clear? Is this okay to everybody? Guys, please tell me if you are getting the idea. If it is not clear, then please let me know, and if it is clear, then also let me know. Okay. So, okay. So, if you have understood this, then you just need to understand that the trivial and semi-non-trivial, FDs are not important. Yeah. If you have a semi-non-trivial FD, then you can divide it into two FDs. You can divide it into two FDs. So, let's see. If I have an FD AB implies BC, then I know that by splitting rule, I can actually divide it into two parts, that AB implies B and AB implies C. So this AB implies B is actually the trivial part of this FD. This AB implies B is the trivial part of this FD, and this AB implies C is a non-trivial part. I hope you understood that that why we call it semi-non-trivial. Why? Because it consists of non-trivial portion, but along with that it also consists of some trivial portion. So this is it. Chalo. So let's try to understand one thing. Let's have a question. Consider the following relational instance. What am I providing? Instance. Consider the following relational instance. So this is some relation R which consists of three attributes A, B and C, and the values are, let's assume something like 1, 1, 1, 2, 2, 1, 2, 3, 1, 3, 2, 1. So these are some values Now what am I asking is, what non-trivial FDs may be present? What non-trivial FDs may be present in the relation R? Why may? Why may? Because this is just an relational instance. Its value may change over the period. So at this point of time, you may think that okay, this might become a functional dependency, but after a point there may be some insertions in the table which will force you to think that okay, this functional dependency cannot exist in this relation. Got the idea? So just think of this. Just think of this question. If this is any random relational instance, then what non-trivial FDs may be present in the relation? So let's try to understand the concept. Sir, first try to write down all non-trivial FDs with respect to three attributes A, B and C. So possible non-trivial FDs with three attributes A, B and C are. So what are the possible things? Sir, there's a possibility that when we have A, one possibility is, sir, A can determine B. Similarly, A can determine C. So these are non-trivial. You can actually see that left hand side is not the superset of right hand side, and the intersection of 2 is actually 5. Intersection of 2 is actually 5. Apart from that, you can say, sir, B can implies A, B can implies C. Similarly, C can implies A as well as C can imply B, right? So these are the FDs. Now, these are with respect to single attributes. Now you will say, sir, perhaps possible that AB together can give you the information of C, or AC together can give you the information of B, or BC together can give you the information of A. Tell me, are there any other non-trivial FDs possible? Okay, let me try to explain that, then I'll rule it out. That you may say, sir, that A implies BC may be present. Similarly, B implies AC may be present. And similarly, C implies AB may be present. So what's the idea? If you are saying A implies BC is present, if you are saying A implies BC is present, then it effectively means that A implies B as well as A implies C will be present. So if both of them are present, then you already know that this FD is present. If both of them are present, then you already know that A implies BC is also present. But okay, fine, note down. You can actually have it in your list because these are the possible sets of X and Y such that X is not a superset of Y and X intersection Y is equals to phi. Can you write any other thing? Can you write any other thing, or can you write FDs in any other manner such that X is not a superset of Y and X intersection Y is phi? No sir, not possible. No sir, not possible. Right or wrong? So now check. What, sir? If at all this FD is present, if at all this FD is present, then whenever the values of A are same, the values of B should be same. Whenever the values of A are same, the values of B should be same. So let's look at this, that in this two tuples, value of A is 1, but the value of B are not same. Values of B are not same. Right? Therefore, this functional dependency cannot exist in this relation. This functional dependency. What did we say? That if A implies B exists, then whenever the values of A are same, the values of B should also be same. If we get any two tuples in which the condition is not matching, then the FD A implies B will not exist in the relation, right? Now, what about A implies C? Values of A are same and values of C are not same. Therefore, this also is not a valid FD. Sir, wherever values of C, look here, the values of B are same. So, when the values of B are same, values of A are also same. Do we have any other place where the values of B are 2? No, sir. So, the values of B are same. In that case, the value of A is also same. So, the value of B is 1. There is no other tuple in which the value of B is equals to 1. So, if condition itself fails, therefore, you don't need to worry about then condition. Here, the value of B is 3. There is no other tuple in which the value of B is equals to 3. Therefore, if condition fails, that T1.x should be equals to T2.x. So, if T1.x is not equals to T2.x, then you don't need to worry about T1.y equals to T2.y, right? So, for B implies A, this condition is true. That is, B implies A may be a possible non-trivial FD in the relation. Now, if at the latter point of time, why am I saying may be present? Why am I saying may be present? Because after some time you may insert one tuple in which the value of B is 3 and the value of A is also 3. So if this happens, then the value of B will remain same, but the value of A will not be same. So if it happens, this will also be ruled out. This will also be ruled out. But at this point of time, there is no such situation. At this point of time, there is no such situation. Now, what about B implies C? Value of B are same, but the values of C are not same. Therefore, again, B implies C is not a valid FD. What about C implies A? Wherever C are same, the values of A are not same, right? So, go on. Wherever the values of C are same, the values of B are also not same. So, done with this. Now, AB. Okay, AB. So, values of A and B are 1 and 2. So, do we have 1 and 2 anywhere else? Yes, sir. Value of A and B are 1 and 2. So, value of A and B are 1 and 2. Value of A and B are 1 and 2. It means the value of attributes at A and B are same. Then the value of attributes at C should also be same. But it is not the case when the values of A and B are 1, 2. In the first tuple, the value of C is 1. When the values of A and B are 1, 2. In the third tuple, then the value of C is 2. Therefore, this is not a valid non-trivial FD. Now let's look at AC implies B. So just look at this. So AC. So this is 1, 1. This is 1, 1. Do we have 1, 1 anywhere else? Do we have 1, 1 anywhere else? No, sir. So if condition itself is not satisfied, therefore you don't need to worry about then condition. This is 1, 3. This is 1, 3. Do we have 1, 3 anywhere else with respect to A and C? No, sir. Do we have 1, 2 anywhere else with respect to A and C? No, sir. Do you have 2, 1 with respect to A and C anywhere else? No, sir. So this is a valid, this may be a valid non-trivial FD. Last BC about BC to A. So 2, 1, 1, 3, 2, 2, 3, 1. All are different. Therefore, this is also a possible non-trivial FD. Got the idea? This is also a possible non-trivial FD. We are not considering this blue color tuples in the relational instance, right? Now, you can actually see A does not determine B, A cannot determine B, neither A does not determine B as well as A does not determine C. So, this is obviously not possible. Similarly, B determines A, but B does not determine C. B determines A, but B does not determine C. Therefore, this is again not a valid non-trivial FD. C implies A, no. C implies B, no. So, this is again not a non-trivial FD. So, non-trivial FDs which may be present. Non-trivial FDs which may be present in the relation are, what are they? Sir, how many FDs did you get? Sir, B implies A is a possible FD which may be present. AC implies B and BC implies A. BC implies A. Got the idea? So these are the three non-trivial FDs which may be present if this is the relational instance. All other non-trivial FDs will definitely not exist if the relational instance is of this particular type. Clear? So that's just the normal idea of defining the non-trivial FDs for a relation. Now let's move further. Now we are coming to the topic of properties of FD. So what do I mean by the reflexivity property? What do I mean by reflexivity property? What is reflexive? So let's see. If an attribute A relates with A itself, if an attribute A relates with A itself for all the attributes, then we say it is reflexive. Yes, reflexivity, reflexive relation. I hope you understand. So you just need to understand that X implies X is a reflexive FD. Which will always be valid. So what do you mean by this particular property? That okay, every attribute can determine itself. What's the meaning of this property? Every attribute can determine itself. That's the meaning of this property. X will determine X is a reflexive FD which will always be valid. Why? Because X is the superset or equals to X, and a trivial FD will always be valid in any relation. Now next is third, transitivity. What does it say? It says if X determines Y and Y determines Z. So X can give you the information of Y and Y can give you the information of Z, then the values of X and Y will be of such type that the X will be capable of giving the information of Z. So if X implies Y and Y implies Z, then X implies Z. This is the normal transitivity property. So if X implies Y and Y implies Z holds true, then X implies Z will also hold true. Clear? Augmentation. What do you mean by augmentation? Augmentation is related to adding something. Augmentation is a property in which we add something. So what does it say? If X implies Y, then you can augment an attribute set in the both side of the FD. So you can say XZ implies YZ holds true. What does it mean? It means to say that you can augment the same attribute on both sides of the FD. What do you say? We can augment the same attribute at both sides of FD. So, but you cannot do so that, sir, I am augmenting Z here and W here. You cannot do so. You cannot augment two different attributes on two different sides of the FD. You can augment the same attribute at both sides of FD. Clear? So this is nothing but augmentation. So what else? So union. What does it say? So union tells me that if X implies Y, let's try to understand this. If X implies Y and X implies Z, if X implies Y and X implies Z, if both of them are true, then you can union this FDs. That is X implies YZ. That is X implies YZ holds. Right? Because X can imply Y as well as X can imply Z. So you can eventually club them, that X implies YZ. You can club them. So this is just the union. What is splitting? Splitting tells you the opposite thing of union. Splitting tells the gives the opposite information of union. What does it say? If X implies YZ, if X implies YZ, then what can you say? Then you can say X implies Y and X implies Z. X implies Y and X implies Z. But splitting can be done only at the right hand side part. What's the idea? Splitting can be done only at the RHS side. So, splitting can be done only at RHS side. What do you mean when I say only at RHS side? That means if XY implies Z, then if XY implies Z, then you can split the LHS. That okay, I can write X implies Z and Y implies Z. This need not be true. Need not hold true. So something which need not hold true, we cannot define that as a property. Why? Because X and Y together can give you the information of Z. So what do we know? X and Y together can give you the information of Z, but it does not mean that X alone can give you the information of Z or Y alone can give you the information of Z. Got the idea? So splitting cannot be done at the LHS part. Splitting can be done only at the RHS side. So these are the 5 properties of functional dependency. That okay, that X implies X will exist, that is reflexive FDs will always hold true in any relation. What does it say? Reflexive FDs will always hold true in any relation. Transitivity says if X implies Y and Y implies Z, then the values of X and Z will also hold the property that X implies Z. That whenever the value of X will be same, the values of Z will be same. Right? Similarly, augmentation, if X implies Y, so X can, what's nothing. So it's actually saying X can give you the information of Y. X can give you the information of Y. Then you are saying XZ can give you the information of Y. Now try to understand. X can already give you, X is capable of giving the information of Y. If you have added Z in the determinant set, then you can obviously determine Z along with the Y because X was capable of determining the Y, and now you need to determine one extra attribute, that is Z, but the information of Z is available in the determinant set itself. So you will be able to determine it. Now similarly, union X implies Y. So here we are trying to say that X can determine Y and X can determine Z. So if X can determine both X and Y, if X can determine both Y and Z, then why don't we write it as X determines Y and Z? Why don't we write it as that X determines Y and Z? Clear? Similarly, splitting rule is again the same, that X implies YZ. That means X can give you the information of Y as well as X can give you the information of Z. So if this is the scenario, then you can split it, that X can give you, X can tell me about Y and X can tell me about Z. Clear? Table having more than 3 attributes, finding valid trivial FD, taking very time consuming. Get easy CSE. First try to understand one thing. I'm just giving you one information that you cannot determine the FDs based on the relational instances, but based on relational instances you can rule out the FDs which may not be present in the relation. You can rule out the FDs which may not be present in the relation. Therefore, there is no point of checking this. So, sir, then why did we discuss this? Okay, let's see. The idea is you guys knew some other things as well. Therefore, you ask such type of question, right? So this information will be useful in identifying the FD set of a sub-relation of the original relation, but this information will not be derived. This information will not be derived based on the relational instances. This information will be derived based on the FD set of the original relation. Will be derived based on the FD set of original relation. So you don't actually need to solve this type of thing, that what happens if there are 4 attributes or 5 attributes. I definitely understand that the number of FDs for which you will have to check will increase. So it will take more amount of time. That's but obvious. But the problem is that why are you trying to understand that particular thing? So that will be just a permutation and combination, that how you can arrange 5 attributes on 2 sides of an arrow. What's the idea? How you can arrange 5 attributes on 2 sides of arrow such that no attribute of right hand side is part of the left hand side and there is no common attribute between them. So this is just a question of permutation and combination. We are not trying to solve that particular thing, right? But the idea is that my motive was to only explain one thing, that we do not derive the functional dependencies based on the relational instances. But if we have relational instances, then we can definitely have some intuition that what may be the possible FDs of this particular relation. But the actual FD set will be defined only on the complete knowledge of the attributes of that particular relation. Okay, so don't try to mix two different things. You will not have to do it for 5 or 6 attributes. No, not. I mean, there will be no question in which that will be needed. So these are the different properties of FD. Now let's move to a new thing, that why. So that's the title of the video, that why do we need functional dependencies? That is, what is the importance of functional dependency? That's what we are trying to understand. So one thing is that functional dependency are key dependencies. So we can determine keys based on the functional dependency. So that's one benefit of that. That is one benefit of that. But why do we need keys? So that we will learn in the upcoming videos. But one thing which I can say is that we can determine, so you can say functional dependencies are key dependencies. Functional dependencies are key dependencies. Therefore, we can determine keys of the relation based on FD set. That what are the different FDs for that relation based on FD set. But what is more important with respect to functional dependency? Why do we need this FD? Why do we need these keys in the relational database management system? We are trying to achieve something else. What? So just read this definition. Functional dependencies are used during the process of normalization. Why do we use functional dependency? Functional dependencies will be used during the process of normalization to seek out and eliminate the redundancies present in the database. So in your database, so functional dependencies will eventually be used to identify if there is any redundancy in this database or not. And if there are redundancies in that particular database, then we will eliminate those redundancies using the concept of functional dependency only. Sir, why is it needed to eliminate? Why is it needed to eliminate the redundancy? Because the elimination of redundancy will overcome certain anomalies. So we'll understand that what are the different type of anomalies. But guys, just 1 minute. Sorry guys for the disturbance. Okay, so let's move ahead with this particular thing, that why do we need functional dependency. So let's try to understand a situation in which we have a table. So this time you will have to understand this with respect to our table. So let's say that we have our table in which we have the information about enrollment, right? So let's assume that there is the information of student ID. Try understanding this. This is very important for the purpose of understanding the concept of normalization. So this is SID. Then obviously the student will have a name. So you have the information of name. So these attributes, that SID and SNAME, are actually the attributes of student. Yes, there should be a table student. Let's try to understand this, that these are the attributes of an entity which can be defined as a student. Then you can have some other thing. So student will eventually enroll for the courses. A student will eventually enroll for the courses. So you will have the information of course ID, that which student has enrolled for which particular course. This course will also have its name. Then what is the name of this course? Right? So I hope this is the clear thing, that okay, these are two different things, that this SID and SNAME are the information or the attributes of a student, whereas course ID and course name are the attributes of course. That what is our course, right? Let's try to understand this. Now, what's the idea? One student can enroll for multiple courses. Obviously, one student can take multiple courses. Courses are, let's assume, the subject. So you can take operating system, DBMS, discrete mathematics. So let's assume S1 has enrolled for course C1, right? So S1 can also enroll for another course. Obviously, sir. Now, this course S2 can be enrolled by some other student as well. This course S2 can be enrolled by some other student as well as this course C2 can be enrolled by another student S3 as well. Apart from that, this S3 can eventually enroll for a new course, let's assume C3. This is possible, right? This is possible. But what you need to understand is, sir, the name of the student S1 is not going to change. So if the name of the student S1 is A, then it will remain A at all the possible tuples. Now, the name of two different students may also be same. So let's assume the name of student S2 is also A, just for the sake of understanding. And let's assume the name of the student S3 is B. So you can have the values B and B for the S name with respect to C. Now, let's look at this course. So C1. So let's assume the course C1 is database management system, right? And course C2 is your operating system. Course C2 is your operating system. So now tell me, can we have two different courses? So just try to understand this. Can we have two different courses whose course ID are different but the names are same? Can we have two different courses whose course IDs are different but course name are same? Yes, it is possible. Yes, it is possible. Why it is possible? Let's try to understand. Just like there may be two student IDs whose names are same. Similarly, there may be a course C1. Let's assume this course C1 is the course DBMS of computer science branch, whereas this C3 is a same course which is DBMS, but this ID C3 is with respect to this ID C3 is with respect to EC or electrical branch, right? So we can have course names, we can have same course names with respect to two different course IDs. Now, what is the important thing here to learn? Sir, what will be the candidate key of this relation? What will be the candidate key of this relation? Sir, candidate key. Sir, what are the different tuples? So you just need to understand one thing, that one student will not enroll for same course twice. One student will not enroll same course twice. Therefore, one thing is guaranteed, that this S1 and C1 tuple will not appear anywhere else in the table. Similarly, S1 and C2 tuple will not appear anywhere else in the table. So, tuple wise, the values of SID and CID will be unique. tuple wise the values of SID and CID will be unique. Therefore, can I say that SID and CID together will form the candidate key? Now, if there is no other candidate key, let's try to understand the beauty of this concept. If there is no other candidate key, then you will have to define this candidate key itself as a primary key. You will have to define this candidate key itself as a primary key. Yes or no? So, the moment you define this candidate key as a primary key, you have placed one constraint. What? So, if it is a primary key, then what can you say? Because it is a primary key, SID and CID are not allowed to take the null values. This is a constraint. Therefore, SID and CID attributes cannot take null values. Right? Got this idea? Now, sir, do we have redundancy in this particular table? So that's what you need to understand, guys. This is very important. That first you need to identify the redundancies. It's too much noise because of this kids. Sorry. So, what you need to understand that what do I mean by redundancy? So, let's look here. See, the name, this SID is S1, the name of the student is A. So, we already know. So, let's look at this. The name of student S1 is A. So, if the SID is S1, the name of student will be A. So, again, when the same SID is appearing, why are you telling me again that the name of student S1 is A? So, this is duplication. This is redundancy because the same values SID can actually determine S name. Do you know that if you know SID, the S name will be same. You cannot have a scenario in which the S1 have two different names. So if S1 is appearing anywhere in the table, the S name will also be same. So this is one thing, and this is redundancy. Similarly, wherever S3 is appearing in the table, S name will be same. Similarly, whenever this course C2 is appearing in the table, the course name will be same. So these are the redundancies. I'll give you one important thing here. So these are the redundancies. This corresponds to redundancy. Right? But tell me, whether this information that the A is appearing twice, this is the redundancy or not. This thing which I have circled with the red color, this thing is a redundancy or not. Sir, you may say, sir, these are duplicate values. But you just need to understand that this is not a redundancy. Why? Not a redundancy. It is information. What information? It is information. What information? That two different students, S1 and S2, are having the same name. This is not a redundancy because two different students are having the same name. This is the information. Similarly, here also, this DBMS is not a redundancy, because two different courses are having the same name. This is not a redundancy. Got the idea? So these redundancies are present in the relation. What are the problems because of this redundancy? So you need to understand the next thing. Problems because of redundancy. I'll not give you the complete definition. I'll just give you the name. You can understand the concept. I'll give you the I will explain the concept. So problem because of redundancy. So the very first problem because of redundancy will be wastage of storage. Sir, is it really a problem to worry about? No, sir. This is not a problem to worry about. Right? Then what are the more important problems? So there are some anomalies which are known as insertion anomaly. I'll explain these things. Deletion anomaly. And fourth is updation anomaly. What are these three anomalies? So let's try to understand this. Sir, I have told you one thing. What? That SID and CID are the part of what? SID and CID are the part of the primary key. Therefore, they cannot take the null value. Right? Now, let's try to understand one thing. That if someday, if this is the information, so this is the information of a university. This is the information of a university or a college. So, the university may want to introduce a new course in the syllabus. Yes or no? The university may want to introduce a new course in the syllabus. Let's assume that university wants to introduce a course. Let's look at this. Color. Okay, so let's use this. The university want to introduce a new course C4 for artificial intelligence. Very hot branch at this point of time, right? So, but tell me, can you insert the information of this course C4 in the table enrollment until some student register for this course C4? So the idea is, see, if no one has registered for the course C4, then in this two places you will have to write the null value. You will have to write the null value. But what do we know? That, sir, this null value is not allowed because it is a primary key. Because it is a primary key. Yes or no? So, what is insertion anomaly? So, you just need to understand one thing. What? In this table enrollment, there are two different information. One is the information of a student, and another information is the information of course. These two things are independent. These two things are independent. So what you need to understand, that if independent information will be stored together, then the information of course will not relate with the information of a student. So if you would like to introduce a new course in the table, then you will not be able to do so, because you will not be able to insert some other information in the table, as you are not allowed to insert the null values, right? So you will not be able to do so, right? So what is insertion anomaly? Insertion anomaly says that because of independent information, that is student and course, we may not insert some information without inserting other independent info. That is, if you don't have the information, if you are not storing the information of a student, then you cannot store the information of course. So it's one problem. Right? So this is one problem, that is insertion anomaly. And we are eventually needed to insert the information in the database. Why have we created the database? We actually want to store the information in the database. This is the primary reason of creating the database. That is, store the information and retrieve the information. Okay? What is deletion anomaly? What is deletion anomaly? Just for one day. From yesterday it will not happen. What is deletion anomaly? So, perhaps it is possible that some student want to leave the college. Some student may want to leave the college. So, let's assume if student S1 decides to leave the college, what will happen? If S1 decides to leave the college, you will have to remove the entries corresponding to student S1. So, you cannot simply remove the information of student S1 and place null at these places because it is not allowed. Yes or no? So, because you cannot place null values at the place of SID, what you will have to delete, what you will have to do, you will have to delete the complete tuple. Not allowed, therefore, what will you do? Not allowed. Therefore, delete complete tuple. You cannot only delete the information of a student, therefore you will have to delete the complete tuple. Now what will happen? So let's try to understand. A student S1 is leaving. A student S1 is leaving. But what is another thing is being deleted from the table? See, no one else has enrolled for course C1. No one else among the students has enrolled for course C1. If you delete the information of student S1, then you will lose the information of course C1, that course C1 is also available. What the idea? So, because of deletion of some information, we may lose some other independent information because we are not allowed to insert the null values. And this is called deletion anomaly, that the anomalies may occur because of deletion. So, what is deletion anomaly? It says because of deletion of some information, some info, we may lose some other independent information. These are not dependents. We may lose some other independent information as we are not allowed to insert null values. That's again, this is the problem because of key concept. This problem is there because of key concept. That okay, this primary key concept is there, so you cannot put it null. So independent information are there, then ultimately the candidate key of this will consist of the candidate key of both those independent relations. Primary key, so what's the idea? Primary key of this enrollment will eventually consist of the candidate key of this table student as well as the candidate key of this table course in general, right? So both of them will have their part in defining the primary key. So if you delete one information, then you will not be able to insert, if you delete the information related to student, then you will not be able to insert null with respect to SID. If you insert a new course, then you will not be able to insert null at place of SID. So that's the idea, that there are some problems because of insertion and deletion, because this redundancy exists, right? Now the last one is obviously clear, updation anomaly, that the same copy is available at multiple places. If suppose tomorrow if the student S1 wants to change its name from A to X, then you will have to update the changes, you will have to perform the changes at all duplicate copies, right? So updation anomaly is quite simple. Updation needs to be performed at all or in all duplicate copies. Therefore, time consuming. So time is also an important factor of designing the DBMS. Therefore, time consuming. Right? So these are the three problems. Okay, we may live our life with the wastage of storage because this is not that big problem. But we cannot make the database inconsistent. If you are trying to insert something and if you are not allowed to do it, then the database is inconsistent because all the information are not available in the database. Similarly, if you are trying to delete something, so if you are deleting the information of student S1, then you are also losing the information of course C1. This is also not allowed because, I mean, inconsistency, you have lost some information which was there, which is actually present. So course C1 is still present in the university, but it's just that no one is enrolled for that particular course. Therefore, the information of that particular course is not available in the enroll table. But the idea, so this is the idea behind this, that okay, if redundancies are present, then these anomalies will be present in the database management system or in the database. Therefore, to overcome these anomalies, what you need to do? So I'm just deleting this last thing and that will be sufficient space for me. So what's the idea? So to overcome this anomaly, what you need to do? To overcome these anomalies, we need to split the relation. Let's try to understand now. So there are two different types of information. One is the information of student, another is the information of course. Then why don't you create two different tables, one for student, create one table for student, create one table for course, right? So in student, the information will be related to SID of the student and name of the student. In course table, the information will be corresponding to CID and name of the course. Now, what are the different information available in our table? So let's see. The name of student S1 is A. The name of student S2 is also A. Name of student S3 is B. What is the information available with respect to course? C1 is DBMS. Right, C2 is operating system and C3 is also DBMS. Now, the only information which is missing is that which particular student has enrolled for which course. So, you will have one more table which is known as enroll. In this table, we actually need to represent the information that which student has enrolled for which course. So, you will have two fields, SID, that the student with this particular SID has enrolled for a course with this particular CID. So S1 has enrolled for course C1, S1 has enrolled for course C2 as well, S2 has also enrolled for course C2, S3 has also enrolled for course C2 and S3 has enrolled for course C3 as well. So now these are the splitting. Let's try to understand this, that we somehow I know this, therefore somehow I have decomposed the relation. Now let's try to understand, do we have insertion anomaly in this case? Can we insert the information of a new course C4? See, course information is the characteristic of course table, therefore you will need to insert the information of course C4, that is artificial intelligence, only in this course table. right or wrong? So if no one is enrolled for that particular course, it's not a problem, because if somebody enrolls for that, that entry will be available in the enroll table. Currently, we are just inserting the information of a new course in the course table, and it is not creating any problem. It is not creating any problem. Similarly, deletion. If student S1 wants to, leave the college, then delete the information of student S1. Also delete the tuples in which student S1 has enrolled for some courses. So even if you delete this tuple, then also you are not deleting the information that course C1 with respect to database management system is available in the university, right? Earlier, when we were deleting the information of S1, we were also losing this information of course C1. We were losing this information of course C1 because this tuple will be deleted. So there will be no information related to course C1. But now we are deleting the information of student S1. We are also deleting the information that student S1 has enrolled for what courses, but we are not losing the information of student, or we are not losing the information of course C1. Got it? So that's another benefit. Now, updation anomaly is what, sir? Updation anomaly. If a student, so there are no, so you can actually see there is no redundancy. There is no redundancy. You may say, so these are the two A's, but this is the information. These are the same name corresponding to two different students. These are the two course names, same course name with respect to two different courses. So these are not the redundancy. These are the information. Sir, here this is S3. No, this is the information that S3 is enrolled for two different courses. So this is the information. This is not redundancy. Got the idea? So there is no redundancy once we have decomposed the relation enrollment. There is no redundancy once we have decomposed the relation enrollment into these three sub-relations, right? And because of this decomposition, all these anomalies are overcome. All these anomalies are overcome. But the problem, see, how did we perform this decomposition? How did we perform this decomposition? So, in order to perform this decomposition, the thing which will be used is functional dependency. So, what is the importance of functional dependency? That the overall idea in relational database management system will be to have a database management system in which there are no redundancies, so that there will be no anomalies. But the problem is that when we will initially create the database, there will be some redundancies and they will create some anomalies. So then with time we will observe the functional dependencies, that what thing can give the information of what other things, and based on that we will normalize the database. What do you mean by normalization? We will eventually decompose the database so that the redundancies are eliminated. But in order to do that, you will have to know the functional dependencies. So functional dependencies does not only give me the keys of the relation, but functional dependencies play a very important role in the process of normalization. You see, so basically the decomposition will be purely based on FDs only. The decomposition will be based on FDs only. So we'll see that what are the different types of redundancies which may be present because of different functional dependencies and how do we overcome them. But today we have learned what is functional dependency. They give the relationship between two different attribute sets. What are the different types of functional dependencies? Trivial, non-trivial, semi-non-trivial. Then we have seen the different properties of the functional dependencies, and we have also understood why functional dependencies are important from the database management system point of view, because in relational database management system you actually need a database in which there are no redundancy or minimal redundancy. Clear? So that's the idea, that's why we need functional dependencies. So that will be all for this particular video. I guess we have done enough. So that's the overall thing which you should know about functional dependency. I have also explained that what is the normalization. I'll again give you the revision of the same thing when needed. But okay, so this is the normalization. What is the normalization? Normalization is process of splitting the given relation into sub-relations so that the redundancies are eliminated or reduced. So that the redundancies are eliminated or reduced. That's what the normalization is. So what's the prime objective of normalization? Eliminate or reduce the redundancies from the database. That's it. So, and for that purpose, you need functional dependency. So, functional dependency plays an important role in relational database management system. So, that will be all. I hope you enjoyed the video. If you like the content, then please hit the like button. If you are new to the channel, then subscribe to the channel and press the bell icon to get the notification about our upcoming videos. So, that will be all for this video. See you tomorrow in the next session. Till then, thank you very much. Good night. Take care. Bye bye.